So let's recall what we did in the past lectures. We looked at logistic regression, and in particular, if we had a pair x and y, and where y was a 0, 1 valued, so where 0 and 1 were the two class labels, then we modeled, or one assumption was that we modeled the probability given a then we modeled the probability given for the y, given the x and the w, in terms of the logistic function, and it had the following form. So let me write it here as eta times y, 1 plus e to the eta, where eta was just this inner product that we had. So this was the x transposed times the w here. Right? So in x in general was over the reals in some dimension, and then of course the w, the parameter of our model, was also over this. And so of course we can write this in a slightly different form, and so this will be the starting for today. I want to write it in this exponential form. So I want to write it as y times eta, and then I still have this factor here. So this is minus the log of 1 plus e to the eta here. Okay, so I'm just going to write it in this particular form. That's, of course, just an equality. I haven't really done anything. But what we will see is that a distribution that has this particular form. So here y will be here the variable, and then we have some parameter here, eta, okay? And then we have some normalization constant. So in general, we want to write distributions, so densities here of the following form. In general, this will be an inner product here. In this case, it's just a scalar, so let me write it just as eta times y. So in general, these things could be vectors. Right now, these are just scalars minus a of eta. And so densities of this form are called exponential distributions, or distributions that have such a density are called exponential distributions. And we'll see that they have a lot of very nice properties, and in particular, whereas right now here the y was 0, 1 valued. If we wanted to do similar things, let's say for elements that are integer valued, or take maybe real values, then we can basically do exactly the same kind of procedure that we did for logistic regression. In particular, also remember that we try to look at the maximum likelihood criterion, trying to find out what the best w is. All this procedure we can do for this more general family. So this, in the beginning, let's just introduce what this family is, and then we'll get back to this problem and see why this family is useful in our context of machine learning. Okay, and so this will bring us back to this example. So what is the definition? So what we have given here, more generally, we have given here some phi of y. So in general, this will be some, we'll go to some RD. So this will be in general a vector. In our case, phi of y was just the y itself. And we have some parameter, eta. So this is also in RD. Then the p of y of the form h of y times e to the, and so let me first write it as this specific as this inner product. Later on I will just write it in the standard way, but you find this often in the literature written like this. So eta times phi of y minus a of eta. So a density of this form, and so you might want to maybe write here also that this depends on eta, or you maybe put this in conditioning just to say that this depends on this parameter eta here. Something like this is called an exponential distribution. Okay, so it's an element of the exponential family. And as I said, this just means the regular inner product. Okay, so another way I could have written is just the eta transpose times the phi of y. So let's see what are the components in here, right? So in order for this to make sense, since I'm looking, so this is supposed to be a density here, then of course we want that this h of y will be non-negative, right? So that's just some extra density that we have. And so now what are the, so this one here is called a sufficient statistic. And it's called a sufficient statistic, and that's not completely obvious now. It's called a sufficient statistic because if I give you samples that come from that distribution, and so I'll get some samples, y that come from that, then if I compute the expectation or the empirical expectation of these samples, of this vector phi of y, now of course this will converge, to the actual phi of y under this distribution, and that's the only thing I need to figure out later on what that particular parameter eta is. Okay, so if you look at this distribution, if I have this fixed, then this is an extra parameter in here, and that's just a normalization constant. And so it turns out that the only thing I really need to know about the distribution, if I want to estimate from samples what this parameter eta here is exactly this set of vectors. Okay, so at this point, this is not at all clear why this should be true, but I'll just tell you why this is called a sufficient statistic. Now, this parameter here has many names. It's called a cumulant. It's also called the log partition function. Now, this might be even more mysterious. Okay, it's also just the log of a normalization constant. And so, why is it called log partition function? It's just that for whatever reason, if you give me some function, and this function doesn't, let's assume it's over the discrete or continuous one, this function doesn't sum up to 1, you will need a normalization, right? So if you had written it in a different form, let me write it out. Maybe if you had written here e to the eta transpose times phi of y, and I had forgotten, let's say, I'd not written down the normalization, then in general, if you integrate it out over all values of y, or if y is discrete, if you sum it out over all values of y, that sum or integral in general will not be equal to 1, right? And so you will in general have to have this z, and for whatever reason, I have to blame the crazy physicists for it, okay? They have distributions of this form that play a very important role. They're typically called Gibbs measures, and so they call this z, for whatever reason, the partition function, okay? Just the name. And since this a is just the log of that, it's called the log partition function, okay? Again, just the name doesn't really play, the name itself doesn't really play a major role here. Now, okay, so there's something that's curious about it. As we'll see, is that in general, this is just a normalization constant, and you would think that a normalization constant is not very important, right? If I give a distribution, all that matters is that it sums up to 1. But it will turn out that if we're thinking of that distribution as a function of this parameter here that we have eta, that a lot is encoded just in this normalization. Okay, so we'll talk about, for example, that this normalization constant will be convex, and that will be very important if we do things like here, the maximum likelihood criterion that will make it computationally efficient. We'll talk about what happens when we take derivatives of this with respect to eta, and we'll see that the derivatives encode the moments of this distribution, etc. Okay, so that's kind of certainly funny in the first time you see it, because you wouldn't assume that the normalization plays any particular role. So let's first see that there's some densities that we can actually write in that form and that we think are of interest, right? So what will turn out is that this form leads to many computational interesting parts, and many things can be encoded in it. But we first need to see that some distribution that we actually care about can be written in this way. So let's do examples. So let's first take Bernoulli. And let's convince ourselves that a Bernoulli distribution can actually be written in this, right? So a Bernoulli, the y, I'll still keep writing it y, but even though it's written y, it just takes on two values here, 0 and 1. And so P of the Bernoulli with some parameter mu, where the mean, so it's a Bernoulli distribution with mean mu, right? Then this can be written as mu to the y times 1 to the mu to the 1 minus y, right? So if the probability that it takes on the value 1 is mu, right? I just write mu, often it's written as p, but I write mu because I want to stick with the parameter mu. So this is for when I'm thinking that the probability of y is equal to 1 is equal to mu, right? Then I can write it, this probability in this form. If you stick in here 1, so this should not be condition of mu, sorry, it should be y condition of mu, right? So if you plug in here 1, then you get mu, and if you plug in here 0, then you're going to get 1 minus u, which is, of course, the standard Bernoulli. And so now we want to write it in exactly this form that I wrote down here. So all we do is we bring things in the exponent. So we write it as e to the, we take the log. So it's y, the ln of mu, right? And then we're having plus 1 minus mu, 1 minus y, sorry, the ln of 1 minus mu. And now I want to write this, still simplify this a little bit further. So I have e to the y, and I take this part here and the part with the minus y. So this will be the ln of mu over 1 minus mu. And then I still have left plus, what do I have left here? Plus the ln of 1 minus mu, right? So now I claim that this is exactly of this form, right? So I claim that this is exactly of this form h of y times e to the, so in this case, let's see exactly what this is. So I claim this eta times phi of y minus a of eta. And now we have to specify what these parameters are, right? So, so what is the, the phi of y, in this case, is something very simple. It's just the y itself. And then what is the eta here, right? It's just the thing that multiplies this here. So the eta is here just the log of the mu over 1 minus mu, right? And so now let's just do a small side calculation. So if I have eta is the log of mu over 1 minus mu, so then it means there's e to the eta, right? It's just this. If I multiply it out, then I get e to the eta is equal to mu of 1 plus e to the eta. And it means I can invert this relationship, and it means mu is just equal to e to the eta over 1 plus e to the eta. Okay, so I'm just inverting this relationship. We'll see in a second why that is nice. And so let me just call this function here g of mu. And this function here is called the link function. Link function. Okay, so let's specify the rest. H of y in this case is just a constant, it's just 1. And so then we already written down the inverse here. So mu is just g minus 1 of eta, which is just our logistic function of eta, right? And so the only thing that we still need to specify is the a, right? So what is it if we now compute the a? So let's write it down. So we have the a of eta is what, right? It's just the log of 1 minus, it's just a minus the log, right? So I'm just specified it. If you look up here, I wrote a minus in front of the a. That's just, you know, just how we specified. So I have a minus here, and then I have 1 minus, and then there is the mu. And so now for the mu, we said this is e to the eta over 1 plus e to the eta, right? And so, of course, the top will just cancel. I have 1 over, right? And so this whole thing is just ln of 1 plus e to the eta. So it means we have a of eta is the log of 1 plus e to the eta. Okay? So, looks about right? No? Yes? Head scratching? Yes? Can you speak louder than I? Repeat the last one? What does he mean, repeat? Saying what it means? Okay. So a of eta is the log of 1 plus e to the eta. Okay? Yes? Okay. I'll try to write louder. If you speak louder, I'll try to write larger. Okay? Is this a deal? But you have to remind me. Okay? Maybe this helps. No? I thought you're still young and have good eyesight. No? What happened? Oh. You see, I'm a magician. Now you think it's all perfect. You know, this is just a ploy to get you to think I have good handwriting. Good. So. So at that point, it might be completely unclear why we do this. You know, after all, you know, what could be simpler than writing things here? Okay, we just have taken something simple and written it in a very complicated way. Okay, and so since it was so much fun, let's repeat this for some other ones. Okay, and see. So let's do another one. Poisson. And so, you know, typically a Poisson would have parameter lambda, but I want to write it again as a Poisson with mean mu, okay? And so, again, the P of the Poisson here, and again, I take the y to be the integer. So this lives now, of course, on y to be the natural numbers. So what is this now? P of y conditioned on, again, my parameter mu. Right, so what is the Poisson distribution? Well, we have on the bottom, it looks a little bit funny because y is typically, you know, a real number, and these are now integers here. It's y factorial, right? And on the top, what do I have? I have mu to the y, and I have e to the minus mu. Right, so that's the Poisson distribution here of parameter y, and so of parameter mu, and the y is an integer. Okay, it just looks a little bit strange. Typically you would use I and lambda, okay, but we just want to write it in this form. So this is even easier. So let me write it in this form. I have y factorial, I leave this outside, and then the rest I take to the exponent, right? So what do I have? I have here y times the ln of mu, and then I have here a minus mu. Right? So I've just written it in this form. And so now let me do again the same thing. So let me specify all the parameters. So what do I have? The phi of y is again y. Okay, looks a little bit boring. We always have the same thing. Then the h of y, now it's more interesting, is 1 over y factorial. So that's more interesting. And then what other parameters do we need? We need the eta, right? So I want to say that this is again of the form I want to again write it in this form. So, so what do we have? The eta here is very simple, right? The eta here is the ln of the mu. And so this means that the mu is just e to the eta, right? That's also very simple. And so we have called this one, let me just write it down in the next one. We have called this always the g of mu, right? So this is the link function. So the link function is this. And so the inverse eta is, mu is e to the eta. And this is g minus 1 of eta. And what else do I have to specify? I have to still specify the a. And a of eta, right? So what is a of eta? It's mu, yes? 1 over, sorry? I did twice the 1 over. Thank you. Okay. So what is the a now? The a is simply the mu, but mu is just e, according to this, e to the eta. Everyone on board? All we're doing is just, people shake their head. Would be better to shake it like this, okay? Okay, what is the problem? This is just calculation, okay? All I'm doing is, I'm writing it in this stupid form. We have no idea why, okay? We'll figure out why for the rest in the 2 hours. Okay, so right now, we're just doing the computation, and all you have to agree that I can write it in this horribly complicated form. Everyone agrees? Okay? I mean, it doesn't matter now, right now, if it's plus, minus, these things are in the notes and you can check that later, right? But the point is we want to write this distribution in a form where we have a function that only depends on y. And then here we have an inner product of, in general, a vector with another vector. This vector depends only on y. This vector is a parameter vector. And then we're having a normalization constant. That's how we want to write it. So far, so good? Any fundamental questions or? Okay, so we'll do still one more, okay? And then I'll tell you why we're doing it, okay? But we need to go back to these examples. So another good one is, of course, the Gaussian, right? So Gaussian, of course, has a mean mu, and will have in general a variance sigma squared. So it will have two parameters. So just look at what we had so far. We had two one-parameter families, the Bernoulli, which is only one parameter, the mean, and the Poisson, which is also just one parameter, which is the mean. And look at what D became, right? What became the dimension of this phi of y? What was the dimensionality of these vectors? It was one dimension. Okay, so that means something, okay? Because we need one parameter to specify it. We just specified it in a different domain. Now, how many dimensions do you think this vector for the Gaussian will have? Wild guess. 2, right? Because there are two parameters. And so presumably we have two parameters, the mu and the sigma squared. And now eta will have to have two parameters. And it will turn out they will be related in some complicated way. But we will be able to go back and forth. So it's just a reparameterization of the Gaussian. Okay, so let's do this. So again, what does it look for the Gaussian? P of the Gaussian of y. And so now we have the mu and we have the sigma squared. Right, so what should I write here? What is the standard density for the Gaussian? Someone tell me. 1 over loud. 1 over 2 pi sigma squared. Square root times e to the minus, right? Y minus the mean over 2 sigma squared. Okay, now again, we want to write it now in this form. So let's do this, right? So we expand everything out here. So what do we get? We get a minus, and then we're having a y squared, right? And then we're getting here over times 1 over 2 sigma squared. Oh, let me write it in another form, just sorry. 1 over 2 sigma squared times y squared. Okay, so this is by expanding out just the y term. Then I get 2 times the inner product, right? And I will get now a plus, because I have here a minus and a minus. I'll get a plus, and there will be a y. And what I'll have here is a 1 over sigma squared. Right? And then I have a mu on top. Right? So I get 2 times y times mu over 2 times sigma squared. So let me just write it like this, and then this. And then I still want to bring this up, the normalization constant, right? So what I'll do is I write it as e2, so I get a minus because it's 1 over. I get a half because I have a square root. And then I have the ln of 2 pi sigma squared. Fine? So again, all I've done is just expand it out. Nothing really interesting. So now let me write it down like this. So I have now here 2 components, a y and a y squared. Okay, so let me write it down in exactly this form. So this will be, there's no factor in front, so I write it as a 1. So the h of y will just be 1, will be trivial, right? Let me not even write it. And then I have here e to the, and so I want to have the vector. So I will have an eta 1 and the eta 2, and we'll have to see what these vectors are, right? Times, and now the phi. So what is now the phi vector in this case? Phi of y is?
What about the mu squared?
You're missing a term.
I'm missing a mu squared. Thank you very much, okay? All these things missing, I get a minus, and then I have a mu squared over 2 sigma squared. Okay, thank you very much. Okay, I'm missing. Good, so what is now the phi in this case? I want to write it as an inner product. So what will be the eta 1 and the eta 2? The eta 1 and the eta 2 will be exactly these 2 coefficients here. Okay? So I need to multiply them with what? I need to multiply them with a y and with a y squared. Okay? And then I still write minus a of y. A of eta, sorry. So now let's still write down all these parameters. So let's see. Eta 1 is the one that multiplies the y, which is just the mu over sigma squared. Then this is eta 1. Eta 2 is the one that multiplies this, is minus 1 over 2 sigma squared. Right? Then phi, we already wrote down, phi of y is just a vector that's y and y squared. Right? And so now let me just write down the inverse functions. Let me just copy it here. So we can also write the inverse function mu is minus eta 1 over 2 eta 2. Sigma squared is minus 1 over 2 eta 2. And a of eta is equal to minus eta 1 squared over 4 eta 2 minus a half log n of minus eta 2 over pi. Okay, it's written in the notes, and just for completeness, I wrote everything down. Yes?
Could you, is phi of y fixed, or could you also choose y squared over 2, and then eta 2 and change?
Yeah, so you can, yes, absolutely you can. Okay, so that's that's kind of your model. So the point will be that for every fixed phi of y, and then maybe an h of y, there's an exponential family with some parameter, right? And so if you do the 2, there's an obvious, of course, a relationship between the 2, but they're not identical. Okay? Even more, what you can do something, in this case, these 2 things, the y and y squared, are not, they're kind of independent if you think of the real line. You could even, okay, and that would be a non-canonical way of writing it, you could even take something where there are linear dependent ones in there and still write it in there. And sometimes that's convenient to do for some reason, but typically we'll stick things where these things are independent, so where this, where then really you get a nice mapping between the 2. Okay? But in principle, that's also possible. So, is it clear? This and many, 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 many other distributions can be written in this form, okay? That's all we want to know right now. And now we want to know why we are interested in these distributions. Okay, so now let's check. We keep these up there because we'll have to come back later. And now we want to understand why we are interested in such distributions. So the first thing is the claim. The first two claims correspond to the fact that if I write things in this distribution, so what we did is right now, we took a density that we're familiar with and we wrote it in this form. But you know, often you go in the other way around. You simply pick some phi of y, could be some vector, right? And then out of this phi of y, maybe also with an h of y in the front, you make up an exponential family. And now you would like to know things about this exponential family. And so the first claim is that if you do that, right, there will of course be corresponding to it for every eta a corresponding normalization factor a of eta. We claim that this a of eta has some very nice properties, and we'll see in the second hour that these properties will exactly allow us to do the equivalent of what we did for the logistic regression, namely write down something, a program, you know, write down some expression that is convex in the parameter and trying to find the best parameter. Okay, so that's exactly the equivalent of what we did for the logistic regression. So the claim is that a of this parameter is convex. Okay, and that's exactly the property that will allow us to learn things in a nice way. So what does it mean it's convex? So well, when we say convex, let's be a little bit more, more precise. Let's say M to be the set of all the eta such that the A of eta is smaller infinity. Okay, so it could happen that, since this is just a normalization constant, what do we have to do to get this constant? Well, you take the expression without the normalization constant, you integrate it out, right, and then divide by this constant to make it 1, right? That's how you make something to be equal to 1. Now, it could happen that when you integrate it out or sum it out, that you get actually infinity, right? And then in this case, you would have this, the A here would be infinity, so that wouldn't make a lot of sense. So we'll restrict ourselves to those parameters, and for our cases, it will always be true, for which this thing here is indeed not infinity. Okay, and so if we're on there, then we're saying it's convex, then it means that for a lambda 1, or for lambda element of 0, 1, and for an eta 1 and eta 2, which where these things make sense, so where things are finite, what do we want to show? Well, we want to show that if we take the point eta 1 and the eta 2, and then we're taking the point eta to be a lambda times eta 1 plus 1 minus lambda of eta 2, right? So then this is the point eta here. So it's just some convex combination somewhere in between, right? We want to show that if we take now this and we evaluate the function in here, so we evaluate this at this point eta, right? Then we want to show that A of eta is smaller equal than the convex combination of these two functions. Right, that's what it means to be convex. Okay, and so now there are several ways how we could do it. We learned already, what are the kind of the two standard ways to prove convexity. Well, one is we can just show this inequality, and we'll do this directly by showing this inequality. But of course, we could also take the A of eta. Eta is in general a vector, and what could we compute? Right, we could compute the Hessian, right? And if we computed the Hessian, and we could show that this was positive, a definite matrix or positive semi-definite matrix, we would show that it's a convex function. Okay, so that's another way of doing it. And just for variety, let's try to show directly this part. So the first thing is to do let's first show what is the, what is actually the A of eta in terms of this expression, right? So we have this expression h of y times e to the inner product of this eta times phi of y. So this is the unnormalized quantity, right? If I now normalize it, so I'm taking the integral here, then, and take the log of this thing, right? So this would be the normalization constant here, but remember the A is the log of this normalization constant, so I've taken the log of this. Everyone clear why the A is the log of this integral here? Right? A is just the normalization constant, or the E, so the E to the minus A is the normalization constant in here, right? So I first take the unnormalized quantity, I integrate it out, and I should divide by that, right? So that would be the integral, but I wrote it not as 1 over z, but I wrote it as e to the minus a, so this means the a is the log of that quantity. Make sense?
Should there be a minus?
Sorry?
Minus.
No, because I divide by this, but I bring it, this is the a, but then I have, that's already correct, okay? Fine? So, now, what do we want to show? So let's write down explicitly what this is. Well, so if this eta now is equal to this thing here, right? So let's expand it out. So if we're now saying this eta is equal to this one here, then let's write this down in a slightly funny form. So we have the ln, right? We have an integral. We have an h of y. And so let me just write it down like this. So the eta here, remember, is the lambda times eta 1 plus 1 minus lambda times eta 2. Right? And this is just a linear function here. So I can write this down as the sum of two terms, one with lambda and one with 1 minus lambda. So let me first take this, the one part that has lambda, put the eta again back in here, the eta 1 back in here. Then this is just, I have here an eta 1 times phi of y. Right? But now I still have a lambda outside, right? So I could simply write the lambda outside, but for whatever reason I want to put the lambda, it's of course the same as putting similarly the lambda in the exponent, and I want to also take this, which has actually an exponent of 1, but write only here an exponent of lambda. Okay, so there will be something missing. Okay, and then let me look at the second part. So the second part, I write again in h of y. And so the claim is that this is now the eta 2 times phi of y. Okay, so all I've used here, that in the exponent, this function is linear, right? That the eta is the lambda eta 1 plus 1 minus lambda eta 2. And so I can write e to the eta times the phi as e to the eta 1 times phi to the lambda times e to the eta 2 times phi to the 1 minus lambda. Okay, and then I still took the h of y, which was just h of y of 1, and wrote it as h of y to the lambda times 1 times a to the y to 1 minus lambda, and just broke it up into two parts. Okay, that's it. So I've not done anything fancy. And now I want to use an inequality, which is called Hölder's inequality, and which goes as follows. If you have functions f and g, and you take the integral over f and g, in general take the integral over the absolute value, but for us everything is non-negative, so we don't need to worry about the absolute values. So in general this simply means you would take the integral of the product of f of g, the absolute value of it. For us these are already the absolute values, they're all non-negative. Then this is smaller than f taking the p norm, and I'll write you down in a second what this is, times f times g taking the q norm, where p and q are numbers between 1 and infinity, and 1 over p plus 1 over q is equal to 1. Okay, so you have these conditions. And so what do I mean if I write here something like f to the p norm? Then this is just, I take the integral, the absolute value of f, by taking to the pth power, let's say this is dy, and they're taking 1 over p thing. Okay, so you notice for the squared norm, right? So if p is 2, right, then this is simply, if p is 2, you just take the absolute value squared, take the integral, and then in the end you take the square root, right? That's just the standard 2 norm, but now p doesn't have to be, so in this case p would be 2, and so you could, for example, take p and q to be both 2, then you would get on the left-hand side the square norm, of the product. Okay? Clear? That's a standard inequality you probably have seen. You probably have not seen it, or maybe not have seen it with the general p and q, but you've definitely seen it when p and q is equal to 2. Okay, so now any suggestions of what we should pick as a p and a q here? Right? So what we want is, of course, this is exactly what we want, right? This is an eta 1 in here, right? And if we integrated this thing out here, right, then this would be exactly, and we had the log still in front, then this would be exactly what we want, would be exactly the a of the eta 1, right? If we didn't have this part and this whole part here. And if we didn't have that part and this part here, then we would have exactly the a of eta 2, right? So that would be useful to have. And so, so now what do we have? Well, so if we're picking here p, so what we will get is here, we'll get here a p, right? We'll get in here a p. So what we want is that lambda times p, hopefully we'll set it to 1, right? Which means that p should be 1 over lambda. And we want that lambda, that 1 minus lambda times q is equal to 1. So this means q should be 1 over 1 minus lambda. And since lambda and 1 minus lambda are between 0 and 1, this means that 1 over their quantities are between 1 and infinity. So that fulfills, is in here. And also we know that the sum of these two inverses here, right, is of course lambda plus 1 minus lambda, which is equal to 1. So everything works out. So this means this is equal to the log, right? We still have the log here, and then we have the integral here of h. I don't need the absolute values, everything is non-negative. So we're having this to the pth power, lambda times p times d mu, dy. And then I take 1 over p. And then I have the other part, which is integral h of y e to the eta 2 times phi of y times 1 minus lambda times q dy times 1 over p, 1 over q. Okay, looks complicated, but we chose it in exactly this way that this thing cancels, is 1. This thing cancels, it's 1. This thing here we recognize as just being, this thing here is just, the e to the a theta 1. This thing here is just e to the eta 2. Okay, just give me 1 second. But then you still have a 1 over p here. Okay, so you still have a 1 over p here, but 1 over p is just lambda. And 1 over q is just 1 minus lambda. And this whole thing is then just equal to lambda a of eta 1 plus 1 minus lambda a of eta 2. Okay? And that's exactly what we wanted to prove. Okay? Miracle. Applause. Okay? Worked out all nicely. Okay? Good. So we'll take a break. When we come back, we'll talk a little bit about it, and we'll look at another very nice property. Maybe we look at derivatives. Okay?